There are lots of different types of mathematical functions and lots of ways of making plots of those functions. Starting with simple functions of a single variable, this uses plot to make a plot of x cosine x for x from 0 to 50. It's possible to show more than one function on the same plot by entering the functions in a list in the first argument of plot. For example, this input shows two functions on the same plot. Many aspects of plots can be adjusted using options. For example, in this input, the plot theme detailed option adds a frame around the plot and grid lines and a legend. The plot style option sets the styles of the lines in the plot. The filling option specifies the shading between the lines, which can be useful for emphasizing the differences between two curves. And the label style option specifies the fonts to use for the labels. A plot with a logarithmic vertical scale can be created using a function called logplot. For example, this shows a logarithmic plot with options to add a frame and grid lines and a label. In addition to logplot for plotting with a logarithmic vertical scale, there's also a function for plotting on a logarithmic horizontal scale, and this example shows log-logplot, which uses logarithmic scales both vertically and horizontally. Another way to make plots with logarithmic scales or with any scale is by using the scaling functions option of plot. For example, here is another plot of that same function, this time using plot rather than logplot, and with the scaling functions option used to specify a logarithmic vertical scale and a reversed horizontal scale, which gives a scale that increases to the left rather than to the right. Plots of parametrically defined functions can be created using the parametric plot function. For example, this shows a basic use of parametric plot where the first argument is a pair of functions giving the parameterized coordinates along the curve, and the second argument gives the range of the parameter. Here's another parametric plot example showing two parameterized curves on the same plot, and the plot theme option set to detailed, which adds a frame and a legend and grid lines on the plot. Here's another way of displaying those same two curves with the transition between the curves specified by a second parameter, which is displayed by parametric plot as shading between the curves. This can be useful for displaying how one function transitions to another. So far, all of the examples have involved functions of a single variable or of a single parameter, but it's also common to plot functions of more than one variable. For example, this shows the plot3d function used to make a plot of a function of two variables. In this result, the value of the function is shown as the height of a surface in 3 dimensions. It's also common to show the value of the function using color or density or using contours. For example, here is that same function displayed using density plot, which indicates the value of the function using color rather than using the height of a surface. That input includes the plot legends option, which adds a legend to the plot. This next input shows a plot of that same function using contour plot, which gives a result that uses both color and contour lines to indicate the value of the function. That input includes the contour labels option set to all, which puts labels on the contour lines and also provides for labels called tooltip labels, which are labels that appear when the mouse is positioned over a contour line. Tooltip labels can be added for other types of plots as well using the tooltip function. For example, here is an earlier example with the tooltip function included to add tooltip labels for the lines in the plot. There are many ways to make useful plots in still higher dimensions. For example, this shows a function called contourplot3d that basically gives a 3D generalization of a contour plot, where the contours are surfaces corresponding to constant values of the function that is being plotted, which in this example is a scalar function of 3 variables. This shows another way of displaying that same function. This uses a function called slice contour plot 3D, which represents the function using ordinary contour plots displayed on slices through a 3-dimensional space. It's also possible to make plots of functions where the value of the function is not a scalar. For example, this uses parametric plot 3D to draw a surface to represent a function of 2 parameters, and where the value of the function is a point in 3 dimensions rather than a scalar. The values of non-scalar functions can also sometimes be represented using color or vectors. For example, this input uses the complex vector plot function to make a plot of a complex valued function of a complex variable. In this plot, the magnitude of the complex valued function is represented using color, and the complex argument of the function is represented by the direction of each vector. Vectors and colors can also be used to make plots of ordinary vector fields. For example, this shows the stream plot function giving a plot where the vectors follow streamlines of a vector field. The direction of each arrow gives the direction of the vector valued function at each point, and vector magnitude is represented by color. A general issue that affects almost all plotting functions is the handling of singularities and outliers. A typical example of that issue is illustrated by this plot, which shows a function with singularities. The function in this example extends to infinity, and some of the computed function values near those singularities are very large, but not all of those values are included in the plot. The vertical scale of that plot is chosen automatically to show most of the variation in the function, which in this example leaves out the very large function values near the singularities. It is possible by setting the plot range option to all to include all of the points that were calculated, but the vertical scale needed to do that is so large that it's impossible in the resulting plot to see anything other than the singularities. Although the default vertical scale may be a better choice in that example, there are other applications where it is important to include outliers or other large values. For example, the default vertical scale in this plot leaves out the large central peak of the function. If that feature is important, it can be included by setting the plot range option to all. Another common and unrelated use of the plot range option is for specifying a fixed plot range when comparing different plots or different functions. For example, here's a manipulate with a slider that controls a parameter in a plot. With the vertical scale chosen automatically, changing the parameter changes the vertical scale of the plot, which makes it difficult to see clearly what the parameter is doing for this pair of functions. A fixed plot range can be specified using the plot range option, which makes the effect of the parameter more obvious and makes it easier to compare plots for different values of the parameter. Returning to the handling of singularities and outliers, treatment of the places where the function is outside of the vertical range of the plot is controlled by the exclusion style and clipping style options. To show how those options work, here's another plot of a function with singularities. In this result, the singularities show up as gaps in the places where the value of the function is outside of the vertical range of the plot. And this shows the same plot with the exclusions style option set to black, which draws black vertical lines at the points where the function is singular, and with the clipping style option used to specify thick red lines where points have been left out. Similar issues come up for other types of plots. For example, here is a result from plot 3D with the exclusion style option again set to black for the singularities and the clipping style option specifying cyan for points above the vertical range of the plot and red for points below the vertical range of the plot. And here is a contour plot of the same function and with the same option settings, again with red and cyan used to indicate regions where the value of the function is outside of the default range, and a black line where the function is singular. Plotting of mathematical functions works by computing lots of numerical values of the function and then plotting the resulting data. For example, here is a result from plot with settings for the mesh and mesh style options chosen to cause the points where the function was evaluated to show up as red dots on the plot. The plot function uses an adaptive algorithm that uses more points near sharp features of the function and fewer points where the function is closer to a straight line. The adaptive algorithm is controlled by the plot points and max recursion options. The default value of these options is automatic. Here's a plot of the previous function but with non-default values for the plot points and max recursion options. The plot points option gives the initial number of points at which to compute values for the function. In this example, that number is 10, which causes the value of the function to be calculated at 10 evenly spaced points. The max recursion option specifies how many times the intervals between points can be subdivided, which in this example is 0, so here those intervals are not subdivided at all. The plot is then constructed by connecting the 10 initial points with straight lines. The values of these options can be increased to resolve fine details in a plot or decreased to make the calculation faster. For example, here's a plot of a function that has a series of sharp features. The sharp features in the actual function are periodic and evenly spaced, but the plot shows gaps where those features happen to fall in between points that are sampled by the plot function. With a sufficiently large value of the plot points option, the plot shows the proper locations of all of those sharp features. The larger value of the plot points option causes the calculation to take slightly longer, but the plot is more accurate. These same principles apply to other plotting functions as well. For example, here's a contour plot with all as the value of the mesh option, which draws a mesh on top of the plot. The mesh shows where values of the function were computed. Values of the function were computed at the vertices in this mesh, and contours were constructed by interpolating along the lines in the mesh. Like the plot function, contour plot uses an adaptive algorithm for choosing points, using more points near contours or near curves in the function. A common situation where plotting is speeded up by using fewer points is the automatic use of fewer points in dynamic output while a control is moving. To show how that works, here is that same plot with a parameter added to the function and with a slider for controlling that additional parameter. Clicking and dragging to move the slider causes the plot to automatically use a mesh with fewer initial points and no recursive subdivisions. A visible consequence of using fewer points is a plot with contours that are not as smooth. As soon as the slider is released, the plot is redrawn with the default mesh of points and with more accurate contours. Using fewer plot points allows the plot to be generated more quickly, which provides for smoother redrawing of the plot while the slider is moving. The effect while the slider is moving is like setting the plot points and max recursion options to values, as in this example, that are smaller than the defaults. The automatic use of fewer points while a slider is moving is controlled by the performance goal option of the plotting function. For example, here is the earlier manipulate input, but with the performance goal option of contour plot set to quality, which causes higher values of the plot points and max recursion options to be used even when the slider is moving. This gives higher quality plots while the slider is moving, but redrawing of the plots is not as fast. That's the end of the examples. In the Wolfram documentation, the guide page on function visualization provides a comprehensive list of functions for different ways of plotting mathematical functions, and the tech note on graphics and sound provides a more tutorial discussion of the same functions and lots of examples.